Hi everyone. Now, before we start learning about series and parallel circuits, we're going to need a quick reminder about voltage. Now remember that when I have a cell here that has 6 volts, what I'm really saying is that for each coulomb that leaves this battery is giving it 6 joules of energy. Okay, so here's my coulomb, okay, and it's carrying a bag, that's a bag, believe it or not, with 6 joules of energy. Okay, and as my coulomb goes through the circuit, it's going to lose all these joules, so that when it goes back here, his bag is empty. Okay, so my coulomb has 6 joules, he will lose some here, he will lose some here, and by the time he's back here, his bag will be empty. Now, the first thing that we need to remember is that this thing here is a conductor, and a conductor has no resistance. And because it has no resistance, it means that our charges can slide around here freely. They don't care whether they're here, 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 or here, because this is like an ice skating field. Okay, they can just move around. It costs absolutely no effort, because it costs nothing to go around. They lose no energy going around here. Which means that if the potential here is 6 volts, the potential here has to be exactly the same, because this thing will lose no energy going from here to here, from here to here, from here to here. So at any point at a conductor, so all around here, the potential is exactly the same. So if I tell you, okay, now here the difference is 6 volts, which means that, for example, here I have 6 volts of potential and here I have 0 volts. Okay. Now, if I tell you that the potential at this point is 6 volts, and I ask you, well, how much is the potential at this point here? You should think, well, it's in the same wire, there's nothing in between, therefore it's all at the same potential, therefore the potential here is also 6 volts. So anywhere in this wire, the potential will be exactly the same. Not here, because we have something in the middle. So everywhere here the potential will be the same, but not the same as here. And everywhere here, the potential will be the same, but not the same as here and here. Okay? So this is two things that we need to remind. Well, this is one thing that we need to know about potential. Now, the second thing is, as I said, this guy is going to go around, and it's going to lose some energy here, and then it's going to lose some energy here. And here, it should have exactly 0 joules left. Which means that all its energy, it has to lose between here and here, because this conductor is all at the same potential. So if here it has 0 joule left, here it also has 0 joules left. Now, so let's imagine, for example, that my first battery, across my first battery, there's 4 volts of potential difference. So between here and here, there's 4 volts. This means that my guy will come here and will lose 1 joule for each coulomb that it has. Since this guy has 1 coulomb, this guy will lose 4 joules over here. And now remember, by the time he gets here, he can have no joules left. And he already lose 4. So how many can he lose here? Well, 2 joules. And since, remember that 1 volt is 1 joule per coulomb, it means that the potential difference around here has to be exactly 2 volts. So as you can see, however many volts the battery is giving us has to equal adding up all the potential energy drops through each of the components. Okay, so if this is 6 volts and this is 4 volts, this has to be 2 volts. Alternatively, if I cover these up and I tell you that the drop here is 4 volts and the drop here is 2 volts, we know then that the potential difference between here and here has to be 6 volts. Okay, now we need another reminder, this time about current. And remember that current, the conventional sense, says that there's some charges that go this way, and we call it I. Okay? So basically it just tells us how many charges are going through, for example, this point every second. Now, the thing about charges is that they can't disappear, right? So if I had 10 charges here, I have to have exactly the same amount here, because, you know, they don't get eaten by the wire monster. Which means that if I start here with 10 amperes, and remember that 1 ampere is just a coulomb per second, so if here I have 10 coulombs flowing every second, then here, since they had nowhere else to go, I still have to have 10 coulombs every second, therefore 10 amperes. So if there's 10 amperes in here, then there have to be also 10 amperes in here. Okay? And now we come into a little problem, right? So here's our wire split in two. Some of it goes this way, some of it goes this way. Now here there's no light bulbs, no resistors, nothing like that. But we will put them there, and it will make things more complicated. But the basic idea is always the same. Now I have 10 amperes coming in, and I told you that charges cannot disappear. Therefore, for example, imagine that there's 2 amperes going this way. Think about how many amperes are going this way. Now pause the video, think about it, come up with an answer, and see whether your common sense agrees with me. Alright, hopefully you did this. And well, since I have 10 amperes here and they can't go anywhere, if here I only have 2, the rest have to have gone this way, right? Therefore, here I got 8 amperes. And this is a very important result. This is telling me, because charge is conserved, this is always the same. Every time that my current splits, if I add up all the currents in each branch, I'm going to have the current in the main branch. So whatever comes in has to be equal to what comes out. If I make this a little bit more abstract, let's just call this I and call this I1 and I2. So this is the first current, well, the main current, first current, second current. We have that I has to be equal to I1 plus I2. And this is just common sense, and you don't need to memorize this. All you need to know is that charges cannot be destroyed. If I start with 10 charges here, I have to finish with 10 charges here. Now, the first type of circuit that we're going to talk about is a circuit in series. And in series just means that we put things one after the other. This could be a light bulb, a resistor, whatever it is, but we put them one after the other. There's only one wire, and we put things in that wire. Now, the first thing that I ask myself is, okay, so for example, if I have a potential difference here of 8 volts, will the potential difference across each one of these guys be more or less than 8 volts? Now, give yourself 2 seconds to think about this. Pause the video if you want. But the answer, of course, has to be that the potential difference across each one of these will be less than 8 volts, simply because, as I told you, when we add up the potential difference here and the potential difference here, we need to get 8 volts. So each one of those has to be less than 8 volts. So these will typically be less bright than, let's say, just putting one light bulb in here. Because this light bulb will get 8 volts, whereas these two will get less than 8 volts, and therefore their brightness will be less than this. So this is not very handy, and that's the reason why we normally don't put the lights in our house or in a car in series. Now there's another reason, which is that if for whatever reason this light here goes out or this light bulb here goes out, what I have then is an open circuit, and the electrons can't go through. And if they can't go through, they can't reach this light bulb, which means that this light bulb is also going to go out. So this is not very handy. If I have 2 light bulbs and one goes out, I would very much like for the other one to continue glowing. This is not going to happen when I have 2 light bulbs in series. Now, apart from this, we can actually calculate some things with this. And that is extremely important and extremely handy. Now, common sense wise, I have 2 resistors here, 2 light bulbs. And I don't really want to have 2 because, calculations are hard when you have 2 things. But I could think about, okay, so if I know the resistance of this guy, and I know the resistance of this guy, how much resistance do you think they will have together? So if I just ignore the fact that there's 2 things here, and I just consider this as one big resistor, let's call it RT for total resistance, how much resistance do you think this thing will have? Now pause the video and say a formula aloud, and let's see whether you got it right. Well, hopefully your common sense told you that this should be easy, right? So yeah, if I have this resistance and this resistance, I have 2 of them, then I should add them up. So this one plus this one would be the total resistance, and you would be right. So in series, and careful, this only happens in series, the total resistance is just the sum of the resistances. What if I have 20 resistances in series. Well, then I just add them all up, like the 20 of them. Easy peasy. Now, I can prove this to you, but I don't think it's worth it. This is a consequence of the fact that the voltage drop here and the voltage drop here have to add up to the voltage here. I do encourage you, though, to try this out as an exercise, and it's going to be part of the black problems when we do this in class. Now, another option for making a circuit is to use a parallel configuration. A parallel, as you can see, is just, instead of putting things one after the other, I split the wire in two so that some of my charges go this way and some of my charges go this way. This is actually very, very handy, and that's the way we connect things at home or in cars, and we'll see why. Now, the first thing that we need to remember is that when we're in a conductor and there's nothing in between, all the points are at the same potential. So let's say that this is 8 volts again. Well, if we have 8 volts here and 0 volts here, this point is at 8 volts, and so is this one, and this one, and this one, and this one, and this one. So all of this is at the same potential, which means that the potential difference between here and here is exactly the same as the potential difference between here and here, and here and here. So the potential difference between here and here is exactly 8 volts, and also the potential difference between here and here, which means that when we place things this way, we don't lose any potential. Remember, when it was in series, we had less than we got. Here, not at all. This has 8 volts, this has 8 volts. So what will happen to the brightness of the light bulbs as compared to if I put them in series? Well, here I have more potential, and therefore they will be brighter. So this is very handy, because if I put my light bulbs like this, they all get the same potential, and therefore they will all be equally bright, and not brighter than if I put them in series. But not only this. Now, what happens if this light bulb goes off? Well, if this happens, all that happens is that this part of the circuit gets broken, but the charges, they can still go this way. And if this one goes out, then they can still go this way. Which means that if one of them goes out, the other one keeps working. And that's what you want, for example, in your house, right? Because if one light goes off and then the rest of them do, then you're in trouble, especially if it's at night. Whereas if one light goes off, but the rest of them keep working, well, things are much better. Same thing for a car, right? If one of the lights of your car goes off, it would be very nice if the other one didn't. So this is why normally when we use light bulbs in cars, houses and stuff, we put them in parallel. We don't lose any voltage, and we have the added benefit that if one of them goes out, then the other one keeps working. Also, I could add a switch, right? So I could, for example, put a switch here and a switch here, and then I would be able to switch off these two things independently. Or I could put another switch here, and then I could switch them off together. But it's my choice how I decide to do things. In series, I don't have a choice. If I put one switch, they both go out, period. Now, just like we did in series, we would also like to know the total resistance that these two light bulbs or resistors or whatever it is that I put here have together. So again, I'm going to call this one R1 and this one R2, and I want to know the total resistance, which I'm going to call RT. And this time things are not so easy, because you can't just add them up. And the reason is that when I put resistances like this, I'm actually I'm giving electrons more ways to travel around the circuit. So I'm actually making it easier for them and not harder to go around. So what I should expect is that the total resistance is less than either of those. Now, there is a way to calculate this, but it's not simple. I'm going to try to prove this to you. I'm pretty sure you will get it, but then when people do calculations, they tend to do all kinds of weird stuff. So let's go step by step. Now, the trick here is to use what I told you before. The fact that if I have some intensity coming this way, then it splits into this one and this one. So let's call this I1 and let's call this I2. And we know that the total intensity, the total current, is equal to this one plus this one. And remember, all I'm saying is that whatever comes this way has to then split here and here, and nothing gets lost and goes somewhere else. Now what we need to do is remember this equation that we have seen many times before, and it says that the current through a certain piece of circuitry, like this resistance, is equal to the PD across it divided by the resistance. And this is really easy to remember, guys. The more potential difference, the more that the current charges want to go through, therefore the more current that I'm going to have. The more resistance, the harder it is for the charges to get through, therefore the less current that I'm going to have. Okay, so let's use this equation over and over and over again. Now, first thing, for the total intensity. Now, for the total current, what we have is that this should be equal to the voltage, which we know is 8 volts, or whatever I put in here, divided by the total resistance, RT, which I don't know. So let's just write that down. So we have that the total current is the total voltage. I'm not going to assume it's 8 volts. I'm just going to write V, because don't worry, at the end it's going to go out, divided by the total resistance. Okay. Now the second thing is what happens here. Well, here I also know the voltage. It's exactly the same as here, because remember that all these points are at the same voltage. So this V doesn't change. But this resistance is R1, and this current is I1. So I have current I1 going through here, stops at resistance R1, and current I1 will be equal to V over R1. Let's write that down. So I have that I1 equals V, again the same because it's in parallel, over R1. And I can do exactly the same thing for R2. Again, V is the same, the resistance is R2, and I2 has to be equal to V over R2. So let's just write that down. I2 equals V over R2. And now what I need to do is use these three formulas and combine them with this formula here. Just substitute. So plug this one here, plug this one here, plug this one here, and I'll get the formula for adding up resistances in parallel. Alright, so let's do that. So, good. Now we have this over here, and I'm just going to rewrite it. Instead of I, I'm going to write V over RT. Okay, so V over RT, remember that's my big I, equals, now instead of I1, I'm going to write V over R1, because these two things are equal. Okay, so V over R1 plus, now instead of I2, I'm going to write V over R2. V over R2. And now you can easily see that this V here repeats itself. So I can divide the whole thing by V and get rid of it. Now if you don't know what I did, this means that you need to brush up on your math. Come to see me, or Mr. Jones, or Miss Fan, or whoever it is, and ask them how this works. Or ask me how this works. So we divide everything by V, so we get 1 over RT equals 1 over R1 plus 1 over R2. And that's the formula that gives us how to add up resistances that are in parallel. Remember, this only works for resistances in parallel. In series, we just add them up normal. Let's do an example, because people tend to get a little bit confused with this formula. So here I have my formula, and let's see, for example, that I have two resistances in parallel. Okay, so this one is 2 ohms, and this one is 4 ohms. Alright, and I need to find the total resistance RT, which is a combination of both. So all I need to do is apply this formula. Let's go step by step. Now 1 over RT, which is what I don't know, equals 1 over R1. I can choose either of them. So I'm just going to choose 4 to be R1, 2 to be R2. 1 over 4 plus 1 over 2. Now hopefully you guys know how to add up fractions. If you don't, worst comes to worst, just plug this into your calculator and add the numbers as decimals. Whatever it takes. Now, fortunately, I do know how to add up fractions, and I know that I need to get the common denominator. So this is 1 over 4 plus 2 over 4, which is equal to 3 over 4. Now, am I done? Is the total resistance 3 over 4? Pause the video and say yes or no. Well, if you said yes, then again, you need to brush up on your math. Because all this is saying to me is that 1 over RT, so let me just write that down, 1 over RT is 3 over 4. But I'm not done yet. This is 1 over RT, not RT. I need to turn this around, and then turn this around, and then I'll have the result. So really, RT is 4 over 3. So remember guys, you're not done when you add these two up. You're done when you add these two up and then flip this around. Because when you add these two up, what you have is 1 over RT and not RT. Please bear this in mind. This is a classic mistake. Everybody makes this. And it's a really easy way to lose points. Remember to turn this around. Oh, and one more thing. I made a mistake here. Give yourself 30 seconds to try to figure out what the mistake is. Pause the video if you have to. Okay, well, hopefully you realize that I forgot the units. So, what are the units for resistance? Please tell me you remember it's ohms. And now we're ready to move on. Now, one last thing. This is pretty simple. And it's just what happens when we add cells instead of resistors in parallel or series. So let's imagine that I add a bunch of cells. So this cell, and this cell. And they are all 1.5 volts. 1.5, 1.5. Alright, now as you can see, these cells have the same orientation. So pause the video for a moment and think, what do you think is going to happen to the total voltage that these three cells are going to generate? Okay, hopefully you listened to me and you paused the video and you said, well, this should add up, right? Because they're all facing the same way, put one after the other. So if the potential difference between here and here is 1.5, and then between here and here is 1.5, and between here and here is 1.5, then the total potential difference should be 4.5. So when I have cells in parallel like this, all I need to do, sorry, in series like this, all I need to do is just add them up. Now what would happen if, for example, one of these cells was facing the other way? Well, that wouldn't be very smart, would it? Because this way, this cell would be counteracting this one here. So instead of adding up, this one would be subtracting. And then what I would have was 1.5 minus 1.5, that's 0, plus 1.5, 1.5 volts. So be careful. Yes, cells add up in series, but only if they're facing the same way. If I put one the other way around, then, you know, I mess things up. And what happens when I put them in parallel? Well, let's figure this out. Alright, so again, I have three 1.5 batteries, so 1.5 volts each. I'm just going to write it here, each. And I connect them all to one wire. And what I want to figure out is the potential difference between these 2 points, between here and here. Now again, pause the video for 20 seconds and try to give me an answer. Now, if you remembered, what I told you at the beginning of the video was that all the points in a conductor, if there's no resistance in between, are the same potential. So if this point is at 1.5 volts and this one is at 0, then so is this point and this point and this point and this point. And all of these points are also at 0 volts. Which means that if the potential difference between here and here is 1.5 volts, then so is this one and this one and this one. So the potential difference between these 2 points is just 1.5 volts, and that's it. All we need to do is remember that all points in a conductor are at the same potential. Now, so why would we do this, right? We're not gaining any potential difference, so that doesn't seem a very smart thing to do. However, what we are gaining is current. Now, so imagine that this one has 2 coulombs going this way, and this one has 3 coulombs going this way, and this one has 1 coulomb going this way. Well, of course, these guys are moving this way and this one this way. They will all meet here, and here, therefore, I'll have 1, 2, 3, 4, 5, 6 coulombs. So what will add up is the current, which means that if I want a big current, then putting my cells in parallel is a good idea. If what I want is a big potential difference, then I want to put them in series. Alright, so a quick summary of what you should remember from today. First, V is the same in a wire. So every point on a wire has the same potential. Second thing, I splits, which means that the current coming in is equal to the sum of the currents coming out. Third thing, that in series, the total resistance is the sum of all the resistances that I put together. That in parallel, it's similar but not quite, which is the sum of the inverses of all the resistances give me the inverse of the total resistance. Now, apart from this, we should remember that cells in series add voltage. So when I put them in series, the voltage adds up. If I put them in parallel, then the voltage is same, but the current adds up. With this, you should have more than enough to solve the 3 or 4 questions after the video. Good luck.